recording now? Does it start recording? Unclear. Oh, there it goes. Okay. I started a new board for this one. Let me unlock it so I don't flip you, so you guys can flip. So I don't flip your pages. So what was I going to say? Yeah. So we have the quiz at the end, and we're going to start a new section. And the new board, the link to this board is in the chat. All right. So let me kind of just start out with a drawing of what primary decomposition is about. So this is, again, Atiya Tunnel section 4 and section 8, and Demmin and Foot section 15.2. All right. So a picture of a primary decomposition. Okay, so here I'm going to draw the XY axis, so the x-axis and the y-axis, and then I'm going to draw a fat point here. Okay, and so this is a picture of the primary decomposition. So this is a picture of this ideal here. So okay, so let me first of all, before I tell you what the ideals are, let me kind of just show you what these are. So there's two types of primes that appear in this picture. Okay, so this is in A2 over a field K. Okay, so there's these ones here, these things here. These are isolated components. So these are isolated here, and then there's this kind of fat thing here, and then this thing here is embedded. Okay, so what we're going to do is we're going to take ideals and we're going to decompose them into primary. We're going to factor them into primary components, right? Each one of these, there's 3 primary ideals that I've drawn here. 2 of them are isolated, and then there's kind of like these fat point things. I mean, they all could be fat, but there's ones that are contained in the other ones, kind of, and those are called embedded primes. And I'm going to say what these are. And so, what is this one a picture of? So this is a picture of the ideal. Well, x intersect y intersect x minus y, this thing squared. Okay, and so this is like a second order. The one I've done here. So this is the purple part.
That's why you made it thick, that point.
Yeah, that's why I made it thick.
And then can I just check?
Yeah.
If I'm saying this right, that A2 is spec of K adjoin 2 variables.
Yeah.
Okay.
This is spec of K adjoin XY. The scheme, not just the topological space. So there's more information than just the topological space. Topological spaces only know about prime ideals. They don't know about primary ideals. Okay. So this is really about, when I say the scheme, it's really about the ring, right? This is this thing here. If this is I. Okay, so then there's these 2 pieces here. So there's the 2 lines here. And so this is a drawing, I guess, of if this is I, then this drawing here is a drawing of spec of K of XY mod I. Okay, that's what this is a drawing of. All right. So the reason I say that this is almost, so the idea is that this purple thing is almost contained in the red, the x-axis. So I just want you to note that here, if I were to take radicals, right, of x minus 1 y squared, right, I took the radical of this. I'm just doing this to be pedantic. This one's already radical, but it could not be. Right, this thing here is, sorry, this is contained in. And so this is just x minus 1 y. This corresponds to the point, right? So this is a thickening of the point. Right. So it's like that. This thing is almost contained in this one. All right. So what is a primary decomposition actually? So let me just say what a primary decomposition is. And then maybe we'll recall some things about primary ideals. So let's go here. So definition. Okay, so a primary decomposition of I, an ideal in a ring A, right, is an expression well, I looks like Q1 intersect Q2 intersect ... intersect Qn, where, well, one, the Qi are primary ideals, and Pi defined to be equal to the radical of Qi, so this is a prime ideal, are distinct prime ideals. And then 2, this is about this irredundancy. So 2 is making sure that there's nothing, you don't have anything repetitive, is that Qi does not contain the intersection from j is equal to 1. So j not equal to I of Qj. Okay. Sometimes this is called minimality or something. Okay.
J equal or J not equal?
J not equal, sorry.
Is it right? The only difference between prime and primary is like x times y for prime versus x times y to the n for primary being, you know, the thing.
It's kind of like that. So primary contain. So recall that. So this is kind of a boost from a previous theorem that we had. So recall a previous theorem. If so that we had something like this. So if so in general, let's do it like this. So if I is an ideal in A, then I is equal to the intersection of P prime ideals. So such that I is contained in P. Okay, so this was this boost, and then so if this is, I guess, in the Noetherian case, then this looks like P1 intersect P2 intersect ... intersect P, let's say PR, something like this. Okay, so then it means so Noetherian, this implies it's a finite intersection. So note as well that you can always have the intersection be an intersection of minimal prime ideals as well, right? So note that one might as well, one only needs to consider, oh, sorry, this is the radical. Sorry, that was the big point. Sorry. This is the radical of this is the intersection of the prime ideals, right? Then the ideal is the intersection of the primary ideals. Okay, so this is a kind of a boost up from this one here. Okay, so what I was going to say is that note that one only needs to intersect over minimal minimal prime ideals. Okay, meaning that you'll never have pi contain pj, because if you had this, you would just throw away the pi. Note in this situation, intersect pj, it's just pj. So you always just take the smaller ideal. Okay. All right. So this is what what the radical ideals look like. Okay. Now we're back to this. So maybe okay. So let me give some terminology here. Let's see. So I'm just hesitant as to whether how much I should say about primary ideals, because I know that you guys had exercises on this before, but I also know that it's been a while. Bear with me for a second. I'm just going to assume that you guys remember what primary ideals are. They're like powers of prime ideals, but not quite. That's actually not true. That they're going to be, it's not true that powers of prime ideals are not necessarily primary, and primary ideals are not necessarily powers of primes. Okay, but lots of them are. For maximal ideals, I believe that's true. That being said, let me just give some terminology here. But you can think about powers of prime ideals for now, right? So, so given a primary decomposition, so actually, I guess I need to. Okay, so a fact. Let's just do a fact here. A fact. So if Qi is primary, or sorry, if Q is primary, let's just do it like this. We don't need to do Qi. If Q is primary, then the radical of Q, we'll define this to be equal to P, is prime. So it's a prime ideal. Okay, and in this case, we say that Q is P primary, right? For a prime ideal P. All right, so that's what it means to be P primary. So let's go back to here, to our example here. So this thing here is, so in this purple case, right, this is x minus 1 y. This thing here is P primary. Okay. All right. Now I can define what minimal and so what isolated or minimal primes are. So definition. Okay. So so 1. Okay. So 1. Let's say 0. So given a primary decomposition, I looks like Q1 intersect Q2 intersect ... intersect Qn. We say that the primes, let's see, do it like this. Let's say with pi, and we'll define this to be equal to okay, so to be the prime that's the radical of the Qi's. Okay, so 0 we call the the PI's associated primes. Okay. If PI appears in the decomposition, the radical of I, then we call it isolated. Right. So this means that it's minimal. So this is the ones that appear in the intersection here. So we don't throw away, we throw away all the things. So like this one here is not minimal. This is not an isolated component. If it's not minimal, it's called embedded. If it is not, if PI is not minimal or isolated, we call it embedded. And the reason we call it embedded is because of the picture, because of that picture that I showed you. Okay, that you have kind of these things here, where the radical of this is one of these ideals that is contained in here. So note here that the radical of I, in this particular example, note that in this example, so the radical of I, this is just X intersect Y, right? So the embedded primes, right, they go away. Okay, so this is an embedded. So okay, so let me just say also. So we will also call QIs. We also call the primary. Sometimes these are called components, though. The primary ideals above prime ideals. So should I say above associated to prime ideals? I don't know. We also call the primary ideals above, let's say, associated, isolated, and embedded. So meaning that if the radical Q is equal to P, and P is isolated, or let's say associated. Yeah, Rick?
I guess I'm kind of unclear what associated means, just like associated relative to I. It kind of seems
standalone. It just means it appears in the primary decomposition.
Okay, so if you fix a decomposition, and then those primes are in that context, they're associated.
Yeah.
Okay.
The important part is that
it doesn't mean anything unless you're already talking about a decomposition. By itself, it doesn't mean anything. Like prime means something by itself, but
yeah.
Okay.
This is all with respect to a primary decomposition. So yeah, so this is So this is all with respect to an ideal, right? So the associated primes are the ones who primes or primary ideals are the ones that appear in the primary decomposition, right? The ones whose radicals, right? The prime ideals that's a radical of a primary ideal appearing in a primary decomposition. Okay, is that clear?
Yes, yeah.
Okay, cool. Okay, so All right. So like, what are the results that we have? Okay. So now we can talk about computing and things like this. So unfortunately, primary decompositions are not unique. Okay. So do we want a refresher on primary ideals first? Let me just do this example, and then I'll do. Let me just do the main points, okay, and then I'll go towards proving things, okay. So so remark. Okay, so primary decompositions are not unique. Are not unique. Okay, so in particular, the embedded components are not unique. Okay, so here, if we look at the, so let's do this example here. Okay, so this is the y-axis with a fat point, right? So the ideal here that we're looking at is the ideal x squared xy, and then you can check that this thing is this with the fat point here, or you can do x with a smaller ideal here, or sorry, a larger ideal. Okay, but these two intersections are the same, but these two so these two embedded ones, the embedded primary ideals are not the same. These things are not the same. Embedded primary ideals are not the same. Although they're on, but the upside is, the upside to this is that the radicals are the same. So the radical is equal to the radical. So the embedded primaries are not the same, but the embedded primes are the same. Okay, so they're the prime ideal. So the prime ideal. Let's do this, I guess, in green still. So the prime ideal is unique. Okay, so these are this is kind of the negative part of this. There's a positive part of this is that so the two big theorems are that so the theorems are the following. Okay, so so the existence. Okay, so one is that for Noetherian rings, for ideals in Noetherian rings, primary decompositions exist. Okay, two. So this is kind of like uniqueness one. So the primary ideals, the isolated primary ideals are unique. Okay, and three, this is another uniqueness result. Two is that the minimal, sorry, the associated prime ideals are unique. So this is without the fuzz. I guess I shouldn't write that. I should just say that. Okay. So the idea is that, like you can know that there's going to be something above some of these prime ideals, right, that are going to be embedded, but you don't know which, just like in this theorem here, or just in this example here, right? In this example, so this is a primary, so this is an isolated one. The x is the ideal x is just isolated, and then the fat point here, which was embedded, right? Although the embedded primary ideal is not unique, the prime of those primary ideals, so the radical of it, is unique. All right. All right. And so, like, to start working with these, we need to just kind of talk about the behavior of primary ideals under the colon ideal, and this operation called saturation. Okay, so there's kind of a way of picking out components from once you're given an ideal, right?